Okay, today we're going to be looking at the starter code for your Python panel method project. If you follow the link in the assignment description, it will take you to this web page right here. This is on GitHub. GitHub is just a straightforward way for storing code online. You're not going to be interfacing with it too much, but this is where you'll get the code from. So you go to this web page, and there's two ways to do it. For those of you who are familiar with Git, you can clone the repository. This is the link here. Or for those of you who are not familiar with it, you can just click download zip here. Once you've got it onto your machine, let's go and have a look at what is in there. So I'm going to go to where I've stored this. And let's look at all the different files that are here. So I've included a few things just to get you started. There's an example input file. There is a main Python script. There's a meshes folder. So this will contain a few different meshes that you'll use through the project and that you can fiddle around with yourself. There is a panels script that contains classes for modeling panels. Oh, that's not in the repository. That's something I created. Don't worry about that. And then there's a VTK script that handles the mesh importing for you. So let's go ahead and open up the main script and have a look at what that does. So what main does here is it will get the input file. So whenever you run main.py, you'll need to specify your input file after main. So you'll just run python main.py and then the input file that you're wanting to run. And that's what that looks like so far. So it uses the sys.argv variable to get that input file. It'll open it, it'll load it, and it'll store it in a Python dictionary here for you. And then I've already included code to load the geometry for you. It gets the geometry file out of the input dictionary and then runs this load VTK routine, which then will give you back four things. It will give you the number of panels in the mesh, the number of vertices in the mesh, the panels themselves, and then the vertices themselves. Now, we'll get into that in just a second, what exactly those are. And then here in the middle is where you're going to write all of your code. Well, most of your code. A lot of your code is also going to go into the panel script. And then once you're all done, I've started a example output here where you can use this export VTK function to take what you've calculated and put it into an actual VTK for data viewing in ParaView. So you specify the output file based on what's given in the input, and then you'll need to give export VTK the output file, the panels, the vertices, and any results that you want to export. So the way I've written this function, and this should make the life really easy for you, is for any result you want to put out, so for example, doublet strength, source strength, pressure coefficient, surface velocity, you create a dictionary of it. And for each dictionary you'll say name, tell it what it is, say velocity or whatever. Type, you'll need to specify whether it's a scalar, a vector, or a normal. So if you're calculating the normal vector to each one of the panels, you'll need to specify that as a normal. And then you're going to give it a value, which is the actual data. The first dimension will need to be as long as the number of panels. So again, we're outputting one piece of data for each panel, and then just whatever data you've generated throughout your calculations. And if you'd like, you can pull up the VTK script, and you can look at exactly what it's doing, and you can be reminded here what the arguments for export VTK are. If you have any questions, feel free to ask me. So that's the basic structure of what you have to work with. Let's get back to this panels and vertices here. We'll start off with vertices. Vertices is simply a two-dimensional array, a NumPy array, where the first index is the index of the vertex itself, and then the second index is all the coordinates. So if I just wanted to look at, say, vertex number I don't know, 5 in the mesh, and I wanted to know what its components are, that's the way I would index it. Index number 5, all the components. We'll go ahead and run that. And I'm reading in from this sphere mesh that's come with the starter code, and you can see that it's giving me, this is the location of vertex number 5. Don't forget that Python is 0 index, so this is actually the 6th index in the mesh, even though it is vertex number 5. Anyway, so that's pretty straightforward. Panels, on the other hand, is a list of panel objects, and the panel objects are defined in this script, panels.py. You'll be doing a lot of your calculations here within this class. If you're not familiar with object-oriented programming, I will post a link in the description to I will post some links in the description to good resources for becoming a little more familiar with object-oriented programming. But this is something that you should remember from your undergraduate computer science course. Basically, a class is a data object that contains both information and functions. So, for example, a panel, the information it stores is it stores its vertices, it stores the indices of those vertices, and it stores its neighbors, so which panels are next to it in terms of indices. And it can also have functions, so we can define a function as part of this panel class called def print index. And in Python, the syntax is that the first argument is always self, and that is the panel object itself. And then any other arguments that you want to put in come after that. So we could do message here. And we'll put in 3 quotations as brief description of what this does. Prints the index of the panel with a message. And then in here we will do print self dot, oh, we're not actually storing the index of the panel. We'll just print off the first vertex index for now, and then we're also going to print off message. So this is what we call a member function. So we've now defined a member function of panel. What we'll do, what you can do to call that is say I want to call that on panel number 12. So we will go ahead and say panels, select panel number 12, and then call print index, and we'll give a message, hello world, as always. Let's go ahead and run that. And you can see this is that call here. It's printed out that the index of its first vertex is 595, and it's given our little message here, hello world. So that's a really simple example of a member function to a class. You can get much more complicated member functions. Obviously, you know, as part of your project, you'll need to write a member function that does def calc area, and for this one, it will calculate the area, and then you'll do some kind of calculations where you say, okay, I want to store my area, and say that that's equal, and this is going to be some function of your vertex location. So like self dot v naught, the first component of that, minus self dot v1, the second component of that, times yada yada yada. We won't get into that now. That will be part of a later lecture. But this is how you go about adding methods to the panel class. For something like calc area, you can add that to the initialization function. So this def init here gets called every time one of these panel objects is instantiated. So if every time you create a new panel you want to calculate its area, you would just call self.calc area. And that will ensure for you that for each new panel object you create, it will automatically calculate the area. So that's all there is to that. Again, if you have any questions, please ask in class. We'll go over that. And then all that I need to go over after that is let's look at the meshes that are supplied. So I'm going to go ahead and pull open ParaView. I've supplied a few different meshes, mostly non-lifting configurations, but also a couple lifting configurations if you decide you want to mess around with that. Well, that's not where I want to be. Here's where we are. Meshes. We'll just go ahead and pull these all open right now. Let's look at the sphere mesh. Oh boy. Oh, it rendered all of them. Okay. Okay, let's start off with just the sphere mesh. This is a basic sphere mesh that I've created for you. This you'll be using a lot. Spheres are nice because, as you already know, we know the analytic result for the pressure distribution over a sphere, and so we should be able to calculate pressure distributions over a sphere using the panel method and compare it to the analytical result, and we can see how accurate we are and stuff like that. For other testing purposes, I've also given you a few random spheres. And these are ones that I just created using a script that just randomly distribute vertices and then connect them all into panels. You can see it's got a relatively even distribution of panels, but these panels are all different sizes, unlike this sphere here. You know, they're nice and uniformly distributed. They're really well behaved. These are less well behaved, and this is to give you some insight into what are the meshing sensitivities of your method. Not all panel methods are created equal. Not all formulations are equal in terms of how sensitive they are to mesh resolution and things like that. There's a couple other ones that you can fiddle with. There's a commercial fuselage here. This is one that I got from some of our research partners. But just kind of a, pretty standard jet transport type fuselage. There's a wing that you can mess with. Like I said, as part of the actual panel method project itself, we're not going to be getting into wake modeling. If you wanted to get an actual accurate picture of the flow around this wing at an angle of attack, you'd have to model its wake. And any and all of you are welcome to do wake modeling for your final project. In fact, I would encourage it. It's a really fun, honestly, it's a really fun problem, and I think you would learn a lot from it. But again, this one's supplied in case you want to fiddle around with it. At zero angle of attack, you can run it through your code no problem, because there's no wake shed at zero angle of attack, and you should get good results. And then I've included, just for fun, if you really want to test your code, here's an engine nacelle with a sharp trailing edge. Again, you're not going to get great results out of this one unless you're modeling a wake coming off of this. You can imagine kind of what we've got all around here is we've got an airfoil at an angle of attack, and so there will be vortex shedding here at the end. But you can run it through your non-lifting code and just see what comes out. Again, I really want you guys to be able to mess around with this. Please feel free to explore, test the limits, try and break things. The more you do that, the more you will learn. And that's all for this video. Again, please let me know if you have any questions. And I hope that you have fun with the actual coding part of this project.